Okay, so welcome back. It is my pleasure to introduce the second speaker of this edition of the BRAG, Samuel Boissière from the University of Poitiers, and he will speak on a family of birational models of generalized Kummer fourfolds as coverings of a projective force, please. Please, Samuel.
Okay. Well, thank you for your invitation. It's a pleasure for me to be here. So I would like to present you a work in progress, but almost finished, I guess, in collaboration with Gregory Sankaran and Marc Nieper-Wisskirchen. So let me start by explaining the main object of study of this project. Well, there is a little intersection between the end of Alessandra's talk and the beginning of my talk. But let me recall what I need to explain for this talk. So the main object of study are the same as Alessandra's talk, IHS manifolds. So irreducible holomorphic symplectic. And let me just recall what it means, that there are Kähler manifolds. Compact. So it's such a variety X. Kähler compact and non-singular. Simply connected. And with one global holomorphic two form that is everywhere non-degenerate. So the space of section of the space of holomorphic two forms is one-dimensional and generated by one form, which is, of course, closed because it's scalar. And what is important is that this form is everywhere non-degenerate, so it is a symplectic form. Everywhere non-degenerate. And why do we care so much about these varieties? It's because of the Bovid-Bogomolov theorem. So importance comes from the Bovid-Bogomolov theorem. That says that every Kähler manifold with a trivial first Chern class, for every such variety, there exists a finite étal cover such that Z decomposes as building blocks. The first building blocks, the easy building blocks, if you want, are Calabi-Yau's manifolds, the strict ones. And then products of those IHS manifolds, much difficult to obtain. And then the last factor with a torus. The examples that I will need in this talk, I will not give a whole list of IHS manifolds. It would be impossible at it of the known deformation classes, but I will just present the one that I will need today. The first ones are K3 surfaces. They are the only two-dimensional IHS manifolds. Then the Hilbert schemes of points on K3 surfaces. So Hilbert schemes of n points, which are the moduli spaces of unordered n tuples of points on a K3 surface, which are, and we take the compactification given by non-reduced subschemes. And more important, what Alessandro already introduced, the generalized Kummer variety of an abelian surface. So this is a generalized Kummer variety of an abelian surface A. So for me, everything will be projective here in this talk. So let me recall the construction that Alexandra already explained. So we start with an abelian surface, and we consider the addition law of n plus 1. You will see in a minute why n plus 1 points on A. So this is addition. Of course, this addition is commutative. So we can divide. I will kill them all. Divide by the action of the symmetric group, acting by permutation. I consider the addition law as from this Cho quotient. Let me call it nu. So I will use it a lot. So I will call it the symmetric product of n plus 1 points on A. What happens is that this variety has the singularities. So we consider the Hilbert-Shaw morphism that resolves the singularities. Let me call it H. So it is a Hilbert-Shaw morphism. And the resolution is indeed given by the Hilbert scheme of n plus 1 points on the abelian surface. This is not an IHS manifold simply because it is not simply connected. What was the definition of the generalized Kummer variety consists in taking the fiber over 0. So here we have the origin, or A. And here inside, we will take the Kummer. It's n and not n plus 1. This is always a strange notation. That is the fiber over the origin, so it has dimension 2n, so it is h mu minus 1 of 0. Since this variety has dimension 2 times n plus 1, we take the fiber over the origin, so this high dimension, the Kummer variety has dimension 2n. What does it do? It parameterizes n plus 1 points on an abelian surface such that the addition, using the addition law on the abelian surface, is 0. Why do we call it a generalized Kummer variety? Simply because if we take Cum1 of A, this means that we consider 2 points on an abelian surface such that the sum is 0, so it is 1 point and its opposite, but we keep the information of being a two torsion point, meaning that it is a resolution of the quotient. So cum A is the Kummer surface. That is, it is the minimal resolution of the quotient of A by plus minus identity. So now the question that motivates us I would say like motivated us because as usual we start with a motivation and at the end we do something else, but inspired by this motivation at the end, okay, whatever it gives is not related to the motivation. If we start with an IHS manifold, let's say projective, take X, a projective IHS, and we fix an ample polarization that we call L an ample class. So deformation theory tells us that one can construct a moduli space of deformation of this pair of an IHS manifold of deformation of the pair of X with its polarization. So deformation of the complex structure of this pair. And in fact, let me call it M. M is a quasi-projective variety. This is a work of Gritsenko, Hulek, and Sankaran. Well, just for the story, it is considered as a classical result, but Gregory Sankaran told me, please do not say that it is classical because I'm not old enough. Well, it is still a classical result. So the question that motivates us is, can we parameterize the general element of such a moduli space? This means what I mean with that is to know if this moduli space is unirational. Let me give you a very easy example, maybe the easiest example, possible example. So these moduli spaces will be decorated by the deformation class of the IHS manifold and numerical invariance. So let me start with an easy case. The moduli space of Keith resurfaces with a polarization of degree 4. Moduli space of degree 4 polarized Keith resurfaces. So with an ample class of square 4. By deformation theory, we know that the dimension of this moduli space is 19. But we also know a very big family inside this moduli space given by quartics. So this is the dimension by deformation, and we have the family of quartics. The family of quartics, it is a linear system O4 divided by the action of projectivity, so PGL4. Let's compute. This linear system has 34 parameters, and PGL has dimension 15. And so the family of quartics has dimension 19. So what we find here is that this moduli space is unirational because we have a description of the general element on this deformation space. So M K3 4 is unirational. So now, there are some unirationality results that are known. So some unirationality results have been obtained. And most of them for the moduli spaces of deformations of the Hilbert schemes. And there's most examples for the Hilbert schemes of 2 points on Keith resurfaces, simply because Keith resurfaces and their Hilbert schemes or the deformations have very nice projective models. And so we are able to find, in some situations, a good maximal families of maximal dimension that show that these moduli that describes the general elements of these moduli spaces. Of course, this depends on numerical invariants, such as the degree. So the declaration here would be some numerical invariance. But I don't have to explain in this talk because it's not a talk about numerical invariance. If you want just to fix the ideas, these invariants will be the degree of the polarization, but it is higher dimensional, so it's a degree with respect to the Bovil-Bogomolov quadratic, Fujiki quadratic form. And there is another numerical invariant called the divisibility. It is something related to the latest structure on IHS manifold, but I don't need this. More than this, since these moduli spaces depend on some numerics, the philosophy behind all these examples is that when, I mean, it's not a real statement, it's more what happens in all known examples, when the numerical invariants are high, these moduli spaces are of general type. When the invariants are high. But when they are small enough, these moduli spaces might be unirational. Well, they may be unirational when they are small. And for this reason, we will consider, well, we will not work, we decided not to work on the deformation of heap 2 because, well, there are many examples, but on the other deformation family that we find interesting enough, that is the deformation family of generalized Kummer manifolds. So the framework is to start with an abelian surface with a polarization, but as we see, it's wiser to start with very low numerical invariance. So we take a principally polarized abelian surface. And of course, we take it general in its moduli space, generic in its moduli space. Well, we have two possibilities. We could choose A to be a product of elliptic curves. It is not what we do, but I mentioned this because this has some importance in Alessandra's talk. So if you didn't tell it, so let me tell it. This choice gives the construction of Hernig's manifolds of index 3 and 4. The second possibility, that is what we do in this project, is to take A, the Jacobian of a genus 2 curve. So it happens, again, just by deformation theory, that the moduli space that we are considering here of the generalized Kummer fourfold of A with these invariants, so it doesn't matter, but since we do it, we know it, it's, let me write it. The degree is 12 and the divisibility is 3, just to tell you, okay, we have the numbers. It's already a bit high. This has dimension 4. Yes. But the moduli space of abelian surfaces has dimension 3. This means that we don't have the description of the generic elements. But A, H have 3 parameters. So our objective at the beginning was to say, okay, this moduli space is labeled after a code dimension 1 family, not the generic one. The question is, could we describe the general element of this moduli space? To do this, we would like to find a rational construction of the elements of this moduli space. So the goal is to find a description of these elements using projective coordinates. To find a description of the Kummer fourfold of the Jacobian of a genus 2 curve using projective coordinates. And what I mean with that well, I just erased the addition law, but what we would like to do is to compute, and the principle would be this description of the Kummer variety is not explicit at all. We don't define the addition law, we just take the fiber over 0. It's not projective, there's no computation. We would like to be able to compute the addition law to get, at least birationally, a model of this variety using explicit coordinates. And the point is that this has been done by, in cryptography, it is very classical. So in the inspiration comes from cryptography. For instance, the papers of Flynn, where he computes in coordinates the addition law on the Jacobian. We will do it in a very geometric way, not computationally very. Will be much more geometric, but the intuition that we will use, I will explain you in a minute how it is done. But first, let me give you some statements. Yes. And then I will enter into the details of the notation and give some proofs. So let me state a couple of results that we obtained. So I will put everything together. So with Gregory, Marc, and Gregory. And then I will expand one of these statements. So first thing, so let C be a genus 2 curve. The secret behind this projective coordinate is the linear system of conics on the genus 2 curve. And the fact is that the linear system of conics, cubics, embeds C in a 4-dimensional projective space, but I will take the dual here because it's better for what I have to do. And the dual variety in P4, so C star in P4, is an irreducible hypersurface of degree 14. Somebody said something, but I... Yeah. Oh, I will explain this. Yes. You will see in 2 minutes. It comes. So, second thing, to explain what we have in mind, this Kummer fourfold of the Jacobian of C is birational to a degree 15 covering of P4, this P4, branched along this dual variety. Branched along this star. Let me call it G. This ramified covering of P4 of degree 15. Then, in order to be able to do some geometry on this model, it is better to control the kind of singularities. And fortunately, the singularities are not bad. G is normal. Cohen-Macaulay, Q factorial, and Gorenstein. And one last information. I want to be more precise on what I mean by it is birational to this Kummer fourfold, is that we control what happens. The birational map from G to the Kummer fourfold contracts two divisors. One divisor is contracted to one point, a very special point on this Kummer variety, which is a unique non-curvilinear scheme supported at the origin, to the unique non-curvilinear point of, say, supported at the origin. It is the special point, the vertex of the Briançon variety that parameterizes subschemes supported at the origin. Supported at the origin is trivial sheaf. And one second divisor is contracted not to a point but to a surface. And what it happens that inside this Kummer fourfold there is naturally embedded inside the Kummer variety, the surface of it. And the second divisor is contracted to the Kummer surface of the Jacobian. So that is clearly, trivially embedded inside. So let me now give some details and put some notations and explain you. I would like to explain the construction, first the construction of the covering. First, what is the linear system of cubics? And then how we get a finite covering. And if I have time, I would like to explain the branch lock, why the branch locus is the dual curve, the dual of the curve. So the details now. Let me enter into some technicalities. So I take C, the genus 2 curve. We know that C is hyperelliptic. So it has a 2-to-1 cover to P1. Oh, sorry. That we'll call pi. And so it is 2-to-1 cover. And we'll call sigma the covering evolution. And the branch locus, it is branched in 6 points, 6 branch points. So I can, just to reduce the number of parameters, the first one will be 0, 1, infinity, and then three free parameters. This explains why this construction has three parameters of deformation. So C has the equation of C. So it's a double covering of P1 branch over this. So it is Z squared equals to X, Y, X minus Y. So for these first 3 points, and then X minus A1, Y, X minus A2, Y, and the last one. And the covering involution sigma sends Z to minus Z. So this equation is important because this explains me where I can put this genus 2 curve, and in fact it is embedded in a weighted projective space. Let me call iota the embedding of C in the weighted projective space with weights 1/1/3 of a variable x and y have degree 1 and z degree 3. So it is homogeneous of degree 6. Okay, let me draw a picture. So in the chart y equal to 1, here x and y, so it is like this. And the projection to P1 is branched along this. So we have these 6 Weierstrass points. So 0, 1, A1, A2, A3, and here infinity. Okay, it's better to take a model with 1 point at infinity. It works better for this construction. Okay, so I want to understand the Kummer fourfold associated to this curve, so I take A, the Jacobian of C, and we call the situation of the Kummer fourfold. So I am inside the Hilbert scheme of 3 points on A with the Hilbert isomorphism to the symmetric product here, and here's the addition law to A. We take the fiber over 0. Here inside, I have the Kummer fourfold of A as a fiber over 0. And here, by restriction, I have 3 points on A. Let me say, I put a 0, say whose sum is 0. That is a fiber over it. And let me call it H here again. So what we want from this picture, we want something that is close to the Kummer surface, fourfold of A, but not the symmetric product, because it's below. We want something at more or less at the same level. What we do, we blow up the origin. So let me call it rho and A hat, the blow up of the origin of A. And then, since by functionality of the construction of the symmetric product, I have a map that sends 3 points on this blow up to 3 points on A. I still have the addition law here, and I can consider the fiber over 0 of this map, of this composition. So here it is symmetric product of 3 points whose sum is 0. And I take the pre-image here, and this is the definition of the variety G that I'm considering. So G parameterizes triples of points on the blow-up of A, whose sum is 0, but it's not a sum computed here inside, because it's not a group anymore. It is a sum computed once we blow down the exceptional divisor. And so we get a birational map for free because everything is birational, from G to the Kummer surface, fourfold of A, by factorization of this sim 0A here inside. So you see, it is over this quotient because we blow up with the origin. So from this definition, from this construction, with some work, it is from this description, general description, one can describe what happens, what is contracted in one direction or the other one. It's not what I want to explain. I would like to do more geometry and to explain you the covering. So what happens here? Since A is a Jacobian of the genus 2 curve, here this blow-up is very combinatoric. The blow-up is the symmetric product of two elements on C, and the resolution map from A, from the Jacobian, to the Jacobian is the Abel-Jacobi map. So we take 2 points. We'll write, let me call this P plus Q to say 2 points on C without ordering. And it is mapped to the linear system of P plus Q minus 2 infinity. So let me repeat this diagram to try to understand what is this varieties G and what it does exactly. If I just rewrite it, but more in a more explicit way, more combinatoric way, I take the symmetric product of three. I take 3 points, 3 pairs of points on C. Then, by contraction, I get 3 points on the Jacobian and the addition law to the Jacobian. Here, the fiber over 0 defines me the variety G. What does it do? G parameterizes triples of pairs of points on C whose sum is 0, but when we compute it on the Jacobian. This means triples of points, that is P1 plus P2, first pair of points, plus another set of 2 points, a third set of 2 points, with the property that when I take the addition law, so P1 plus P2 minus 2 infinity tensor P3 plus P4 minus 2 infinity tensor OC P5 plus P6 minus 2 infinity is trivial. And this is what we want to understand in coordinates. So to describe the addition law explicitly. So to do this, the idea is to forget that we forget the ordering, parentheses between these points. So forget the ordering. What I mean is that here, this variety is inside the symmetric product of 3 pairs of points. So again, I take 3 pairs, P1 plus P4, P5 plus P6. And what I want to do is to forget. So I just want to take the formal sum of the 6 points. So I arrive to the symmetric product of 6 points. And I take P1, etc., plus P6. How do I arrive again to the Jacobian? I just factorize this map by the Abel-Jacobi map. So this is, again, another Abel-Jacobi map, a way of saying it, that sends this sum of 6 points to OC plus of P1 plus P6 minus 6 infinity. So here, I have 0, and I consider the fiber over 0. So I want to construct a covering of P4, or what happens. What I want is to understand what is here. And this will be my P4. And this will be the linear system of cubics. Let me explain you why. Well, first, we know from a general result of Matuk, we know that A is a projective bundle. And it is easy to check that, in fact, the preimage of 0 is the linear system of 6 times infinity. And now there is a very classical result of Mumford that explains you what is the linear system of 6 times infinity, exactly, in fact, using the linear system of cubics. Because what he says, I guess I will have time to explain you why it's a very easy computation. 6 points on the curve are equivalent to 6 times infinity if and only if there exists a cubic in P113. So be careful, it's not as usual cubic because it is weighted, so you will see that it is a real cubic as a graph of, from air to air, but not a cubic in the usual sense in P2, such that the cubic intersects C in these 6 points. And this explains why we understand what I meant by computing the addition law on the Jacobian of the genus 2 curve. So let me repeat my picture. What all this means is that six points on the curve, P1, P2, P3, P4, P5, and P6. 6 points on the curve are equivalent as on the fiber over 0, so the sum is 0 in this addition law, if and only if there is a cubic interpolation. And this is the concrete description of the addition law on this Jacobian. Of course, you see that what we are doing here is exactly the analogous of the addition law on the elliptic curve by the lines. But here we are in the Jacobian of the genus 2 curve. They are not lines, but cubics that describe the addition law. And so what all this means is that this fiber over 0, 6 infinity, is the linear system of cubics. And I can now answer your question. What is this linear system of cubics? It is given by the embedding of P in 113. and I take this linear system is a pre-image of all 3 in P113. So because of the gradings, the global sections, what has degree 3 in this linear system? So x, y have degree 1, and z has degree 3. So we have z, x3, x2, z, xy2, and y3. So this linear system is 4-dimensional, so L is P4, and it is my P4 from the covering. What I mean is that here I can conclude 6 points are on the fiber of the origin if and only if there exists a cubic interpolation. So what is over this is P4. It is the linear system of cubics, and the map consists in taking 3 pairs of points and mapping it to the unique cubic of interpolation. Oh yes, so this map from P to P4 is L, sends these points to the equation of the cubic. Well, what does it mean? What is the degree of that? It means that generically it will be the same. So I take 6 points, and I have to organize them as 3 pairs of points. So I take 6. I take 2 among 6. 4 remains. I take 2 of them, and the last one are done. And I divide by the ordering. And if you compute correctly, it is 15. So this covering has degree 15. Okay, I would like to explain you the branch locus of this covering. Now, to explain you, I stated the result saying that this is branch over the dual variety of the curve. Let me explain you that. So the branch locus, the equation of a cubic D, it has equation something like G, forget the variables, alpha 0 z plus alpha 1 x3, alpha 2 x2 y plus alpha 3 xy2 plus alpha 4 y3. And you see, if alpha 0 is non-zero, a cubic, you express z as a function of x and y. So a cubic is really a cubic in the plane. And there are no conics. That's very special for this geometry. The way it degenerates is not with any line and a conic. When it degenerates to 3 vertical lines. So it is very special, a kind family of cubics, in fact. And so we see from that a cubic will always cut the curve in 6 points. And if you, to understand Mumford's results, so this cubic, this equation, divided by y3, this has degree 3. So this is a rational function. And the divisor of this, so they say that G equals 0 intersect C in P1 until P6. This defines a rational function whose divisor is the sum of the points. And the pole is at y equal to 0, you get the point at infinity of degree 2. 3 times it is such, so minus 6 infinity for the pole divisor. And this explains Mumford's results is exactly this computation, telling you that cubic interpolations mean exactly that the 6 points are equivalent to 6 times infinity. And now, where do we have a branch locus? The branch locus is exactly when the cubic has tangency. So the branch locus is a divisor of cubics such that the intersection is non-reduced. So to compute it, what we can do, we can check that this divisor L has degree 6, so L is very ample. And so we consider an embedding of C in the dual linear system, so P5, P4 dual, and the conormal variety of this embedding the conormal variety we see for this embedding is a set of pairs, a point and a cubic, such that the tangent line at this point is contained in D inside, so P, inside the dual here because it's the point on the curve, and the linear system L for the divisor for the cubic. So here, what does it mean? In this embedding, a cubic is a hyperplane section. So what I mean is that this line is contained in a hyperplane. And this condition means exactly that the multiplicity of intersection of C and D is greater or equal than 2. So now I project to L, and the image I project to the second factor. So the image is a set of points of cubics such that the intersection is non-reduced. So the image, the projection of VC to L is by definition the dual of C, and it is exactly the set of points where there is a tangency. And now, well, there are some general results about dual varieties of curves in particular to compute their properties. They are very singular, but what we can see is that C star is irreducible, and we can compute its degree. So there are very general formulas to compute the degrees of these varieties, but in fact, in this situation, it is much satisfactory to take a pencil of cubics. So choose a very degenerate pencil of cubics and compute how many times this pencil cuts the curve with multiplicity. And this gives the correct number, and we find that so to see how many times a line in P4 cuts C star, and we find 14. So this is a degree 14 hypersurface, but it is non-normal. So let me just conclude what we wanted to do was that exactly. We wanted to change the Kummer variety of the Jacobian to something birational that we can control. And we get, so this covering is not Galois, of course, but we can control the kind of singularities that it has and how it is branched. Now I wanted to explain what is the challenge behind this. We still have 3 parameters. So the idea that is still in project is to deform this covering to get 1 more parameter. For the moment, we don't have it, because what we have is a dream. And the dream that we started years ago was to say, if we want to get 1 more parameter of deformation, the idea is that keep the cubics and forget the curve. And for the moment, we have no idea what this means. But we want to make some, it should make sense to get one deformation more. But this will be next time, maybe. Thank you.